I know this can be baffling the first time or the first dozen times. Please ask if you have any questions, try stuff, and see what happens. Here we go, lecture 5.2. Sigma notation. What is it? Why do we care? Why do we care about sums? We'll look at examples and we'll look at properties and formulas. And the properties are already up, so if you want to start transcribing, go ahead. Incidentally, if you are transcribing, maybe don't bother writing this side. Okay, in our very first class, we talked about trying to find the area of something curvy, and we said that was difficult, and we talked about the method of exhaustion, and we talked about inscribing polygons and all this kind of stuff. And it turns out that the solution to the general problem of finding the area of a curvy thing is to look at the limit of a sum, okay? And that problem, the area problem, is the heart of integral calculus. We need to find the limit of a sum, so we need to talk about sums. Okay. If you want to talk about the sum of the first 5 positive, let's do this again. If you want to find the sum of the squares of the first 5 positive integers, you'd write something like this. You'd write something like that. Yeah? Okay. If I asked you for the sum of the squares of the first 100 positive integers, and you wanted to write it like that, you'd crucify me. Okay? You'd probably write something else. You'd probably write something like this. For the first 100. Right? Because no one's got that kind of time. You write 3 dots and you say the pattern continues in the middle. Okay? Suppose you have a variable number of numbers that you're trying to add the squares of. You might write something like this. Okay, the sums of the squares of the first n positive integers, you'd write something like that. Okay? So that's better than, okay, so for this one, it's better than trying to list out all 100. And for this one, you don't know how many there are, so you couldn't do that anyway, so you have to have the 3-dot thing. But that's still imprecise and cumbersome. So we have a special notation to talk about stuff like this. Okay? So, we write, we'll talk about this one, we write, let's do this properly the first time, that beautiful letter, from I equals 1 to 100 of I squared to mean 1 squared plus 2 squared plus up to 100 squared. Okay, so instead of writing that weird thing, we write this precise, concise thing. Okay, we're saying each term looks like I squared, and we're saying the value of I climbs from 1 all the way up to 100. From 1 to 100. Okay? That symbol is called sigma. It's the Greek capital letter S, S for sum.
So I is for like the start number, and then like I squared is like the factoring.
I squared is each piece, okay? So each piece looks like I squared, and this bottom bit tells you where you start, this tells you where you end. Yep? This is not the only way this thing ends up being written, but in this class, that's the only way we'll write it. Yes, sir?
So the I is for like this.
Say one more time.
The I is for like saying that it's only integers.
For this kind of stuff, it'll, yeah, for sums it'll always be only integers. The I, it could be a K, it could be anything. It doesn't matter. It's just a symbol, right, that each term is in terms of. Okay, so each of these terms is a function of that symbol, yeah? And then you say where the symbol goes from and to. It'll definitely only be integers, yeah.
Okay, so it's not like it's always
Yeah, it's always discrete, yeah. It's always integers, that's right, yeah. Yeah, it doesn't have to be called I, but it is always integers. And it's always successive integers, right? So it's 1, 2, all the way up to 100. All right. Okay, that's just one example. In general, we write this. One more time, I'll do it properly. Okay. We write that guy to mean this. grammar there. This means this. Okay? And again, I appreciate this can be dizzying the first dozen times. Okay, that thing is called sigma, or the summation symbol. Okay? I is called your index of summation. Okay? This is a general term. Okay, so the terms you're adding together are the AIs. We'll do examples, and this will be slightly less stupidly abstract in a minute. Okay? Okay. So we're saying we're going to add up the AIs with I starting at m and going through all the successive integers up to n. And that's what this says. So we add a sub m plus 1, up to a sub n. Okay? This is called the lower limit of the sum. This is called the upper limit of the sum. It's not really that kind of limit that we've been talking about the whole time. Okay? So we just say I starts from the lower limit and goes up to the upper limit, and we add all the terms corresponding to that. Okay? Obviously, m and n have to be integers, and m has to be less than or equal to n. Again, we'll do examples. Okay, notice all we're doing is we're adding up the terms in a sequence. Remember, sequences, they have similar kind of notation. That's what's going on. We're adding together the terms of a sequence. Okay. Right. We talked about how sequences are essentially functions. You could think of this in this term as well. You could think of it like this. I equals m up to n. F at I is this. If you find a sequence thing too baffling, think of it the function way. Again, we'll do examples in a second. Okay? I runs from m through all the successive integers up to n, and we add up the corresponding terms. That's all this is. Shorthand for doing that. So let's do an example. For example, if I write this, I equals 3 is the lower limit, 6 is the upper limit, and the general term is I cubed. What does that tell me? It says I runs through the successive integers from 3 through 6, okay, and we add up all the cubes. Okay, that's all this says. So it's saying add 3 cubed, 4 cubed, 5 cubed, and 6 cubed. Okay, get used to the notation. All it is notation. Okay? Another one. It doesn't have to be called I, it can be called J. J runs from 0 to, let's say, n. 1 over 2 to the j. What does that mean? It means add up all the 1 over 2 to the j's for j's running from 0 through n. 1 over 2 to the 0 plus 1 over 2 to the 1, and so on, up to 1 over 2 to the n. This is 1 plus 2, sorry, 1 plus a half plus a quarter, and so on, up to 1 over 2 to the n. Okay? One more example, because something in your end of lesson looks a bit like this, sort of.
So we have to show 2 terms, or like the 3, like for the first 2 shows?
If the pattern's obvious, you can show as many as make the pattern obvious. The point is to make the pattern obvious. And if it's only 3 terms altogether, maybe just show all 3 terms, because maybe you want to add them together, right? Like if it's something like this, you wouldn't really put a dot, dot, dot here. Right? Yeah, that's it. Very good. Okay. Here's an example. Another one. Again, it doesn't have to be I. Let's call it k from -2 to 2 of tan k, just to make it look complicated. Okay, again, evaluate tan k at all the successive integers from the lower limit to the upper limit, add them up, and that's all this is. this, and you'll see why in a second. Nope, I won't write it like that. All right, anyone know what the value of this is? It's an easy number. What's a number you'd have to guess if you're going to guess a number? 0 is a good number to guess. Okay, now you go y. These are all, okay, so what you might do is just punch all this into your calculator and then complain about how stupid the course is, right? Or you can say, what kind of function is tan? Is it even or odd? Is that it? Good, thank you, excellent. Okay, tan's odd. So this guy is the negative of this guy, so when you add them, they cancel each other. Doom, doom. Tan is odd, so this guy is the negative of this guy, so when you add them, they cancel each other. Okay? Tan's defined in all those places. All you're left with is that guy, and that guy's 0, so the answer is 0. Okay? I did that because there's a question on the end of the lesson where if you notice a pattern, you can avoid punching your 14 cosines into your calculator. Just stand here for 10 seconds. We'll stop there, everybody. Have a beautiful weekend. If you have any questions, come talk to me. Any suggestions for the tutorial, tell me. And that's it. A wonderful weekend. Alrighty, we started sigma notation, lecture 5-2 last time. So a notation to compactly write sums. And we talked about why we need it, sort of, and we did some examples with it, and we defined the notation, and we'll start from there. Okay, sometimes you need to be able to go backward. So if you have a pattern or you see a sum, you need to be able to write the sigma notation version of it. So let's do an example like that. And this is something you've done before, the idea of writing a general term for a sequence that you know. So, write using sigma notation. Minus 2 over 9, plus 3 over 27, minus 4 over 81, plus 5 over 242. Okay. You might think about it this way, unless someone wants to tell me something, which is good. Okay. The tops are successive integers from 2 through 5, okay? So, let's write something like this. Write a nice letter. The tops are the successive integers from 2 through 5. So that's what the top will look like. From 2 through 5. The bottoms are the corresponding powers of 3. Okay, 2 over 3 squared, 3 over 3 cubed, 4 over 3 to the 4, 5 over 3 to the 5. And then what? We need to deal with the plus minus stuff. You'll know how to do that or no? Someone shout something if you know?
Minus 1 to the power of n.
That's it, yeah, good, thank you. Excellent, so if you have minus 1 to the power of something odd, you get minus 1 again. If you raise minus 1 to an even power, you get plus 1. Okay? So using that, you can do this. Okay, so if you have, okay, suppose you have minus 1 to the I. Okay? As I goes through successive integers, I will go from odd to even to odd to even to odd to even. And so this thing is going to go from minus to plus to minus to plus to minus to plus. Okay? So using that kind of thing, you get to add your alternating sign in front of it. Okay? However, if we used this guy in front of here, what would we get? So when I equals 2, we would get minus 1 to the 2, which is plus. So we'd start with a plus, but we want to start with a minus. So instead we do this. Minus 1 to the I plus or minus 1. And that's it. That takes care of the numerators, that takes care of the denominators. We've got the right index bounds there, or limits of summation. And this makes sense. Once again, minus 1 to the 2 plus 1, so minus 1 to the 3 is going to be minus 1, so we'll start with a minus, and then on the next value of the index, we'll have a 3 there. 3 plus 1 is 4, minus 1 to the 4 is going to be plus 1, we'll get that plus there, and then we'll keep alternating like that. Okay? So you want the alternation, and you want to start with the right sign. Questions about that? Right. Okay, if you have questions about that, tell me. Okay, and that's that. Okay? Yeah.
So would you write like the odd and even every time you would?
No, I wouldn't write no. In your head. Is that fair? Yeah. You mean like on a paper?
Like with the equation?
This stuff here. Yeah? This stuff you don't have to write.
Okay.
This could be in your brain. Yeah? I'm just saying that this is the tool you use to get the alternating signs. Fair? Yes. Make sure you got something that alternates the signs, and make sure you start with the right sign. Anything? Okay. And there you go. And you've done something like this before. The idea of you've got a sequence and you want to write an expression for the general term. Yeah? Okay. And there is more than one right answer. If you want to talk about that, let me know. Okay? Okay. All right. Here's some properties that are handy when you're dealing with summations. For each of the three properties, we've got it written in sigma notation, and I also wrote the sort of not sigma version of it, so you can see that there's nothing unfamiliar here. This is all stuff you know already. Okay? All you need to know is the notation now. Okay. Let's see. When we talk about a constant is something that has nothing to do with the index. Okay? So C is just something that's got nothing to do with I. Okay. I'll leave it there. Okay, so again, if I write this out expanded, I see something like that. And all that's saying is that you're allowed to pull constants out of sums, which you know already, the distributive property. This guy, again, I expanded out and color-coded so you can see what's going on there. Essentially, you've got a sum of sums of pairs, and what you're doing is you're sort of divorcing the pairs. So you can do that. And this is another kind of breaking up. Oh, incidentally, I should say this. These two guys are the kind of properties you've seen before, right? This idea that you can pull out constants and you can break up sums and differences, which are what makes this guy a linear operator again. So, all right, so like limits, like differentiation, like anti-differentiation, this guy's friendly. You get to pull out constants and you get to break up sums, and that's a good thing. And we'll get to use that soon. And this guy tells you that you can break up sums in a different way. So if you've got a sum of a bunch of terms, you can get that sum by adding the sum of the first chunk to the sum of the second chunk. Okay? If any of this doesn't make sense to you, write it out in expanded form, or try it with numbers, and you'll see it makes sense. Okay? So for instance, for this guy, 2 plus 3 plus 4 plus 5, you can write it as 2 plus 3 plus 4 plus 5. Any questions about this? So write down the properties, especially the stuff on the left. If you're confused, look at the stuff on the right. And try it out yourself with numbers and symbols. Good? Okay, handy summation formulas. Okay, these will be handy. These will be handy later on this class. Let's look at this one. This should make perfect sense. If I add n ones together, I get n. Okay, over here, right? Carbon double bonded to a nitrile group. Yep. Which they'll tell you is impossible. If I add n fives together, I get 5n. It's just that reasonable. Okay? This guy, suppose you wanted to add the positive integers from 1 through 50, okay? Yeah, you can punch in all of that into your calculator, or you can just go 50 times 51 over 2, which is a lot simpler. Okay, and we'll also see in a few moments the value of being able to write an expression for a sum up to a variable. Okay, this one I'll show you how to get to it in tutorial, the others upon request. Okay? So write those down and we'll use them soon. Any questions about this? Okay, I don't know if anyone's going to do this, but just in case, do not do this. Okay, if you're summing up some squares, don't just write that as the square of the sum. Okay, don't do stuff like that. And again, if you're ever confused about sigma notation, you can always expand the sum out and see if that makes more sense to you. And if you're exploring, try it with numbers and see if that makes sense. Or ask me. Questions? Okay. Example. Calculate this. For I going from 1 to 50, 2I, 3I minus 5. Okay. If this was just 3 or 4 terms, maybe you just find each term and then add those terms together and life would be fine, right? For 50 terms, that might be testing your patience, okay? So it might be nicer to use the stuff we just learned. You can pull this 2 out if you wanted to, by the stuff on the last slide, okay? You can pull constants out, so you can do that if you wanted to. Do not try to pull this I out. It's not a constant, okay? So, big warning, don't pull that out. So, don't try to pull the I out. Don't try to break this up. Okay, so don't try to write this thing as this. Do not do this. Do not try to pull the I out. Okay, and don't try to do this either. Okay, that's not a thing. Okay, and if you need convincing that it's not a thing, let me know. Okay? So the things you can pull out are constants, or at least constants with respect to I. Okay. Suggestion? Or do I do it? Expand? Alright, so I'll expand this stuff. You can pull it out if you want to. Because I'm lazy, I'm not going to write this each time, or maybe I'll add them at the end. So what do we got? We got 6i squared minus 10i okay, and we know we can pull out constants and we can break up sums and differences, so then we do that. We'll add all the good stuff in. Okay? And now you see the value of those guys. Okay, once you've broken it up, you can use those guys, that guy, and that guy. Okay. I don't want to do this now. Equals 6 sum I squared minus 10. Good. Okay, so the sums of the squares from 1 to 50, okay, is going to be 50 times 51 times 101. Okay, so we just use that. So 50 times 50 plus 1 times 2 times 50 plus 1, all divided by 6. Okay, minus 10 times the sums of the positive integers from 1 through n is given by n times n plus 1 over 2. So in this case, 50 times 50 plus 1 over 2. Okay? Yeah.
So like, essentially, like, kind of like separated the 6 and the,
Yeah, by the stuff on the previous slide.
so, okay,
Yeah? Yeah, you break it up and now you can use that stuff.
okay,
Good or no?
yeah.
Okay. It's the same stuff you do with limits and with derivatives and antiderivative, yeah? Good. Good? Okay. Triple check. Awesome. Okay, and then you just punch that into a calculator. And you get that inspiring number. Okay? So you use properties to get them to a form or a combination of forms that you have formulas for or you can understand. You apply the formulas and that's it. Easy peasy. By the way, if you calculate this guy or this guy and you don't get an integer, try again. Okay? Sums of integers had better be an integer. Good? Okay, I'm just going to finish by saying that apart from the use we're going to have in this course, sums are ridiculously important in math. Okay, I mentioned Fourier series once. The idea that you can write any periodic function as a combination of sinusoids, essentially. We've also talked about Taylor polynomials, okay, which are sort of linearizations on steroids. And there's also Taylor series, right? And all those guys are essentially sums. Okay, sums are fantastically important. And we'll talk about them a lot in 128. Any questions?